The problem that scientists were having in developing an accurate model of the atom stemmed from they were thinking about electrons as particles when, in order to get an accurate view of an atom, you had to think about electrons as waves. This is what Einstein described as the wave-particle duality of matter. And it only really occurs for things that are very, very light, very, very small, and that are moving very, very fast, which just happens to explain electrons. So you have to consider the wave-like properties of electrons when you're trying to determine what an atom looks like. There's a scientist named Edwin Schrödinger who developed the wave equation for an atom. There it is right there, big, nasty, and ugly. The symbol here stands for the wave function of the electron, and capital E stands for the energy of an electron. Let's try to sketch the quantum model for carbon-12. So it would look something like epic fail. So instead we're going to go on and describe an electron based on 4 quantum numbers. Little picture here kind of shows that these quantum numbers are analogous to like a social security number that every person in the United States has. Well, the 4 quantum numbers are actually assigned letters as well, and the principal quantum number is N, and then the next quantum number is L, and then we have quantum number M and quantum number S. These will have symbol variables, and they will also have numerical variables, as you can see in these cards. So hydrogen and oxygen, that is their 4 quantum numbers listed there. We're going to see how we come up with these quantum numbers and what these quantum numbers mean. Important thing to remember is that no electron has the same 4 sets of quantum numbers when it's assigned in an atom. Let's start by describing the principal quantum number, which has the symbol N. What does this value tell us about the electron cloud? Okay, the electron cloud is the probability area of where we may find an electron. So electrons aren't defined in orbits, they're defined in regions of probability. So these clouds that surround a nucleus where an electron might be, possibly. So what does this tell us about the probability cloud? The N number, the principal quantum number, tells us the size of that cloud. It also tells us the distance that the electrons could possibly be away from the nucleus. The numerical values for N can be any whole number from 1 to infinity. The electrons can have for any given quantum energy level is given by the short little expression 2 times n squared. So 2 times the principal quantum number squared. So if we do this real quick, all right, the first level would be 1 squared times 2, which is 2. And then just follow that pattern as you go. So the next one could hold 8. The third energy level could hold 18. The fourth energy level, 32. And so on and so forth. If we wanted to see what these would look like as a diagram, okay, the lowest energy principal quantum number, so that stands for the shape, it would be the smallest shape. And that should make sense because electrons around the positive nucleus, there's an attraction there. So the closer the negative electrons are to the positive nucleus, the lower energy state they will be in. Okay, it takes more energy to hold a negative charge away from a positive nucleus. So as you go up an energy level and the electron cloud gets bigger, it's higher in energy. And now you have a very good reference that you will use a lot in this unit, and the more fluent you become with using it, the better you will be. So where do you find the principal quantum number on the quantum chart? Okay, it's on the left side of each of the sections that we've broken up for you. So if you look at the quantum chart, the N number is right there on the left side of each of the charts, and the N number is below that label. So 1, 2, 3, 4, 5, 6, 7 over here, 3, 4, 5, 6, 2, 3, 4, 5, 6, 7, and then 4, 5 over here. Okay, so there's where you get your principal quantum number, and it corresponds to basically what row or period of the periodic table you are in.